In this video, we're going to discuss Big O notation, which is a notation used for measuring the time taken to run algorithms. The technical term for this is asymptotic complexity, which you may also see referred to as time complexity and space complexity of algorithms. And this topic, or you could say this issue, is going to be a core theme of this module. And the reason why we're going to be paying so much attention to it in this module is we want to find the most efficient solutions to programming problems. And I'm hoping what we'll see throughout this module is that there is no one best data structure or algorithm that can be applied to every single problem out there. Instead, the performance of each data structure and algorithm will depend entirely upon the context in which it's used. The time taken to run an algorithm depends on how many operations there are within that algorithm, basically how many lines of code there are, and how often those lines of code have to be repeated. And the time taken to run an algorithm also depends upon how many items there are within a particular data structure. Obviously, a data structure which has 10 elements will take less time to sort than a data structure which has 1,000,000 elements. And the performance of some algorithms depends upon the arrangement of items within a data structure. Some algorithms will perform much faster if the items within a data structure are sorted. And there are many other factors as well which influence the performance, such as processor speed, and you'll probably notice differences between the architecture of Mac, Windows, and Linux systems as well. So let's have a look at some different categories for measuring the performance of algorithms. Constant time, which is denoted as O of 1, means that the time taken to perform an operation is not dependent upon the number of items that are within a data structure. So an example of this would be inserting values into an array. There's no difference in the time taken to insert a value into an array of 5 elements compared with inserting a value into an array of 1,000,000 elements. So therefore, this operation can be performed in constant time. Next, we have linear time, which is denoted as O of n, and this means that the time taken to perform an operation will depend on how many items are within a data structure. An example of this would be iterating through a data structure. If it takes 5 milliseconds to access each element of an array, then it would take 25 seconds to go through an array of 5 elements, whereas it would take 50,000 seconds to go through an array of 10,000 elements. So therefore, the time taken to perform an operation is directly proportional to the size of the data structure. Next, we have logarithmic time, which is denoted as O of log n. And put simply, logarithms are the inverse of the power function. So 2 to the power of 3, which is 2 times 2 times 2, gives you 8. So therefore, if we did log base 2 of 8, we would get 3, which is the number of times we need to times 2 by in order to get 8. Okay? And the good news about logarithmic algorithms is that the logarithm only fractionally increases for large increases in n. So you'll see here the difference between log base 2 of 8, which is 3, and log base 2 of 8,000, which is nearly 13. So therefore, by increasing n by almost 8,000 has only resulted in an increase of 9 for the number of operations required for a data structure of that size. And we're going to have a look at applying this principle in an algorithm called binary search later on in the exercises. And finally, we have linearithmic time, which is denoted as O of n log n. Or, in other words, it is linear time, n, times logarithmic time, log n. That means there is a logarithmic algorithm which is being repeated multiple times. Sorting algorithms such as merge sort operate on this principle, where the data structure is repeatedly split in half, which is the logarithmic principle, and then it's merged back together, which is the linear principle. And linearithmic algorithms such as merge sort, are regarded to be some of the fastest ways to sort larger data structures. So moving on to some other measurements, we also have quadratic time, which is denoted as O of n squared, or in other words, O of n times n. For example, if n is 5, then 5 squared, 5 times 5, is going to be 25. But if n increases to 10, 10 squared, 10 times 10, is going to be 100. So you can see here that an increase of 5 for n translates to an increase of 75 for the result of the number of operations or time that's required to run the algorithm. We mentioned earlier that it takes linear time to iterate through a data structure. For example, a for loop that iterates through every element of an array. So if one loop is linear time, O of n, then a nested loop, which is a loop inside a loop, is going to be O of n times O of n. If each loop is linear time, then multiplying them together will give you O of n squared, quadratic time. Therefore, whenever you see a nested loop, think quadratic time, O of n squared. And finally, we have factorial time, which is denoted as O of n exclamation mark. The factorial of a number is calculated as n times n minus 1 times n minus 2 times n minus 3 and so on until the number is 1. So the factorial of 5 would be 5 times 4 times 3 times 2 times 1. And as you can see, the result of 10 factorial is dramatically greater than the result of 5 factorial. And this time measurement typically describes brute force algorithms, which try every single combination, say, of sorting a list or searching for an item, and are generally regarded to be one of the slowest time categories. So definitely best to avoid algorithms of this sort. And on this slide here, you can see how the time taken to run these algorithms scales for the number of items within a data structure. And you can see here that the time taken to run quadratic and factorial algorithms significantly increases as n gets larger. It's best to find algorithms that are logarithmic or linear to operate on large data sets, large data structures. And finally, we should mention that there are best, worst, and average case scenarios to the performance of some algorithms. For example, if we're searching for an item that happens to be near the start of a list, it's not going to take very long to find that item, which is a best case scenario. However, if we're searching for an item which is near the end of the list, where we're going to have to iterate through most of the items in the list to get to the one at the end of the list, this is regarded to be a worst case scenario. And an example of an average case scenario would be an item which is located in the middle of the list, where we only have to iterate through half of the items in the list to find the one which we want to find. So I hope you're starting to see what we mentioned right at the start of the video, in that the performance of these algorithms and data structures depends on a lot of different variables. Okay, so we're going to finish this video here, and in the next video, we're going to have a look at applying these principles to searching and sorting algorithms. So in this video, we're going to take a look at a few different algorithms related to searching and sorting, and we're going to split this into several videos. And first of all, we're going to take a look at the swap algorithm and then have a look at a sorting algorithm. The swap algorithm is going to play an important part in our sorting algorithms and is how we're going to sort the numbers which are out of place in the list into the correct order. We're going to swap the locations of different items. And the swap algorithm is a reasonably straightforward algorithm. It requires a temporary storage location, this could be a temporary variable, to hold the value of one of the items that we want to swap. And then we overwrite that item's value with the other one, and then we use the temporary value to insert into the second location. And the important thing here is that we pass the values in by reference or by memory address rather than by value. Because if we were to pass by value, we would only swap the copies of the original values rather than the original values themselves. we need to make sure that we are swapping the original values. So that's why we're going to set up pointers to these items as arguments for this swap method. So we're about to take a look at our first sorting algorithm, which does apply the swap method that we've just looked at in order to sort the unordered data into an ordered list. And in our examples, we're going to be working with arrays of integers, just to keep things simple. We're going to be sorting these arrays into an ascending order, which start from the lowest number and ascend to the highest number as the elements progress. And of course, the main reason why we want to sort data into an ordered list is that it makes items easier to find. We're going to demonstrate this later when we have a look at the binary search algorithm. But for now, let's focus on the sorting algorithms. And remember back to the previous video, we said that algorithms can be measured using big O notation. And we're going to see here in the SelectionSort that the performance for this algorithm is quadratic. It's O of n squared. And hopefully you remember that means we're going to be working with a nested loop system. There's going to be a loop inside another loop. If each loop is linear, then O of n times O of n is O of n squared. Okay, so this SelectionSort algorithm works on the principle that we locate the lowest value and then swap that with the first element of the array. So you'll see that currently in this list of 5 elements that the lowest element is 1, which is in the second location in the array. So we then swap that with the first location, the first position, which is 5, so that 1 is at the start of the list. Okay, and then we locate the next value, which is 2, and then swap that with the second location to put 2 after 1. Okay, and we repeat this process until the items are in order. So having a look at the pseudocode here, you can see that we do indeed have a nested loop system. We've got 2 for loops, one inside another, the outer loop and the inner loop. And in the outer loop, we're going to be storing the index of the first position, which remember n starts at 0 in this loop. And so we store that in smallest. And then we iterate through the array looking for the smallest value, which we then want to place in that first position, which n or smallest holds, which is 0. So we repeat through until we find that, and then we pass those 2 indexes to the swap method, which we looked at earlier, and then that will swap the positions of those 2 values. And then of course we repeat this until we have an ordered list. Okay, so now would be a good time to have a look at the first exercises, and I'll get you started by walking through the first exercise. Right, so let's have a go at implementing the first exercise then, which is to implement the SelectionSort algorithm. And to do that, we're going to need the swap algorithm. So I'm going to copy that. It's rather handily been provided for us. Going to copy that and paste it within just above main. I'm going to paste it within the project, just above main. And from there, I then have to see the presentation to get the algorithm, the SelectionSort algorithm. So let's do that. Okay, and we'll code this as a separate method. So I'm not going to return anything because we're going to be modifying the array directly through the reference. So let's type this out. We're going to need to create a integer pointer to our array, which has the alias of a, and then a variable for the size of the array. And from there, we're going to start the outer loop from 0 to size -1, and then n++. Okay, and then within there, we're going to need a value for smallest, the index. So actually above there, I'm going to put that there. And then within here, I'm going to assign it to n. What's next? Okay, so then we start the inner loop. We're going to use variable name I. We're going to start n plus 1 and go to size minus 1. Oops, sorry, that needs to be I. And then I++ for the inner loop. Okay, and then next we have a comparison. We're going to compare if a of I is less than smallest, the current smallest value, or the more precisely the index of the smallest value there. And then if we find a smaller value, we then make that, make the index of I smallest, so we update that. End if, end loop, and then swap. Okay, so here's where we call the swap method. And remember, as these taking in pointers, we actually need to pass the reference of an, oops, and a of smallest. Okay, and that should allow that to work with that. Okay, so I think that's all there for our selection sort algorithm. And what's next? Okay, so within main, we need to create an array of integers. So let's do that. And it's just create a standard integer array. Instructed to call it data. And we can use the shortcut for assigning because we've only got a small amount of values, 10, I think, if I counted correctly. Let's copy them in there. Let's check that. Yeah, 10 elements. Okay. And then we're supposed to pass them to the selection sort algorithm, which then sorts them into order. Okay, so what I think I'll do is I'll create a method to print out the array, just so we can print the array before sorted and then after sorted. So let's say print array using a similar signature. We want a pointer to the array and then a variable for the size of the array. And then within here, we'll just have a simple loop which repeats until size minus 1. And then we're just going to output each element. And let's do it on the same line, actually. Yeah. Okay, so now that I've got a method, I can then call this twice. I can call this before I sort. So let's say print array, passing it data, and then number of elements is 10. Let's have a little message to say this is before sort. And then we call SelectionSort, passing it the same parameters, data, our array. And then we want to print the sorted array. And I need to, let's just output a little message to say this is after sorts. Okay, so let's give that a go. See if that works. Okay, so before sort, we see the unsorted array, and then after sort, yeah, we've seen it has correctly sorted our array into order. So there we go. That's the basic implementation of SelectionSort. From there, then, have a go at the next two exercises where you're instructed to create a bigger array full of 1,000 elements and assigned random numbers between 0 and 100, and then I calculate the time it takes to sort this array of 1,000 integers. Okay, so give that a go. Now that we've implemented the SelectionSort algorithm, let's have a look at implementing another sorting algorithm called BubbleSort. And this algorithm still utilizes the swap method, but it utilizes it in a different way. Rather than locating the smallest element in the list and then swapping it with the first element and the successive elements, the list moves on, the BubbleSort compares adjacent pairs of items in the array and then swaps them if the second item is smaller than the first item. And then this algorithm repeats the comparisons until the larger items in the array are pushed towards the end of the array, and subsequently the smaller items are pushed towards the start of the array. But as this algorithm still uses a nested for loop structure, the complexity is still quadratic. But compared with the other quadratic sorting algorithm, which is SelectionSort, there are still time differences, which we're going to see later on when we get to the exercises. So to look at an example of the BubbleSort, let's have a look at this small array here of 5 elements. And we start by comparing the first 2 elements, 5 and 3, and as 3 is less than 5, we swap the values. So 3 is on the left-hand side and 5 is on the right-hand side. And then we compare 5 and 1. And as 5 is greater than 1, again, we swap those. So 1 is on the left and 5 is on the right. And then we keep going until the end of the array, until we get to the last pair. And then we go back to the start and repeat the process again until we get a fully sorted list of elements. And you can see here on the next slide that we do indeed use that nested for loop structure again, where the inner loop represents one pass of the array, and the outer loop will repeat the inner loop until the whole array has been sorted. And in the inner loop, you can see there's a simple if statement which compares the value of one element of the array and then to that element plus 1. So it looks at the next item along in the list of elements. And if the first item is greater than the second item, we want to swap the positions so that the lower items are bubbled towards the start of the array and the greater items are bubbled towards the end of the array. And repeat this process again until the whole list has been sorted. There's also an improvement we can make to the BubbleSort algorithm where we reduce the need to have to compare items of the array that have already been sorted. Okay, and this is achieved by setting up a Boolean flag which alternates between true and false, depending upon whether the items have been sorted or not. And if the items have already been sorted, we don't want to compare them, so we can save time and operations there. But as we're still using a nested for loop structure, the performance of this algorithm is still going to average out to quadratic. However, it may still be a little bit more efficient than the original BubbleSort algorithm. Okay, so let's have a go at implementing the BubbleSort algorithm and its enhanced version and compare the performance of it with the performance of SelectionSort. So for exercise 4, we're instructed to implement BubbleSort. So I'm going to refer back to the presentation for the algorithm for this. Okay, and I'm going to create a separate method above main again for this. Let's write BubbleSort and of course a pointer to our array which has the name A and then a variable for the size, and within the method I want to create an outer loop starting at 0, repeating whilst less than size plus, and then immediately within that I want to create an inner loop j which repeats while j is less than size minus 1. Right, and within that, I want to compare the two pairs of elements. So we'll look at j and j plus 1. And then if the left-hand side is greater than the right-hand side, we're going to swap them. So within here, I need to call the swap method. Again, passing references, remember, because we want to modify the memory address rather than the copy. So we're going to pass it the reference of these two pairs, or two values, I should say, one pair. Okay, that's that, and if and loop and loop and function. All right, brilliant. So that should be that. Let's have a go. Let's test this then. So if I do something similar to before, if I comment out the selection sort in exercise 1, and then rather than calling SelectionSort, we'll call BubbleSort, passing that same array. I'm using the small array just for test purposes, but hopefully once you've done exercise 2 and 3, you'll have the larger array to pass to this. Let's just check this works. Yeah, as you can see there, BubbleSort has successfully sorted them. Okay, so that's good news. So as I say, the thing to do here then is to implement this with the larger array and then compare the performance of SelectionSort and BubbleSort with the large array of these different elements. First of all, it starts at 1,000 and then goes up to 100,000. So compare the performance there, compare how long the time takes. And then once you've done that, try implementing the enhanced BubbleSort algorithm and seeing where comparing the performance with that, with the other BubbleSort and the SelectionSort algorithms. Okay, so give that a go and see how you get on. So now that we've compared the performance of the SelectionSort and BubbleSort algorithms, let's take a look at some search algorithms. And we're going to take a look at two different ones. We're going to take a look at the linear search, otherwise known as sequential search, and the binary search algorithm. Okay, and the difference between the two is that linear search doesn't require the data to be sorted, whereas binary search does. Okay, so let's take a look at the linear search algorithm first. So linear search gets its name because it operates in linear time. Remember that we denote this as O of n in our big O measurements. And this operates on the principle of iterating through the data structure, in our case an array, looking at every element and matching the value of each element of the array, one by one, against the key, which is the item that we're searching for. And if the key matches an item in the data structure, we return a positive value, which in our algorithm, that's going to be the index of the item where it's located in the array. And if we don't match the key that we're looking for, we return a negative value, just so we can distinguish between whether the value exists in the array or whether it doesn't. Okay, so let's have a look at the pseudocode. And you can see here, it's a fairly straightforward one. We're just going to be iterating from 0 to size minus 1, and then comparing the value that we're searching for, the key, with the value of each element of the array. And then if it matches, we return the index, and if it doesn't, we return minus 1. So the algorithm is reasonably straightforward, but one thing to bear in mind is that this is a linear algorithm. So the time taken to run this algorithm is going to scale as the data structure increases in size. So this algorithm is going to be fine for smaller data sets, but in the event of a larger data set, it would be faster to use binary search. But this does require the data to be sorted first. So that's one thing to bear in mind in terms of the total time taken. And providing that the data is sorted, the performance of binary search is logarithmic. It's O of log n. And this logarithmic behavior allows us to reduce the number of items that we need to look at in the data structure by half every single step of the algorithm. Because in a sorted data structure, like an array, we look at the middle value and then evaluate whether the value that we're searching for is either less than or greater than that middle value. If the value we're searching for is less than the middle value, we can ignore that second half, all of the values which are greater than the middle value, because we know that the value that we're searching for is not going to be in that second half. It's going to be located in the first half of a sorted array. And then once we've reduced the data structure by half, we then look at the middle value of that half and repeat the process, splitting the data structure in half again, effectively. And then we keep repeating this process until we find the value we're looking for. So let's have a go at the final exercises, and let's implement the binary search and the linear search algorithms and compare their performance. Okay, so for exercise 6, we're instructed to implement the sequential search algorithm, or otherwise known as linear search. So I'm going to go to the slides and look for the algorithm for that. Okay, and let's implement the method for that then. So notice here I'm actually going to have a return type of int, because I either want to return the index for the value that's been found, or if I don't find it, I want to return a negative value, just so I can distinguish between whether I found something or whether I haven't. So return type int, and then method name, we'll just say sequential search. All right, and then we want 3 parameters. We want a pointer to the array. Actually use the capital A here, but a lowercase would be fine as well. Of course, it's just a variable name. And then we've got the size of the array, and then we've got the key, the value that we're searching for within this array. Okay, and we just want one loop this time because it's linear, so it's going to just look at every element consecutively. So just one for loop. Start at 0 and go to size -1. And then within there, we just have a simple comparison to say that if the particular element that we're looking at has the same value as key, then return the index of that, which will be a positive number, as opposed to at the end, where if we haven't already returned a positive value, indicating that we found something, we then return a negative value, -1. Okay, so from there, I'm going to go back to main, and I am just going to search for a value that's within the array. So that's called sequential search. Passing it data. Still 10 elements. And let's say we search for 3. Okay, and as it's going to return a value, let's store that in a variable. And then we could just have a very simple message to say, if found is not equal to -1, i.e. we found something, then we can say the key exists in the array. Else, if -1 is returned, then we say that the key does not exist in the array. All right, so let's try this then. And there we go, because we're looking for 3. That's been found in the array. And let's search for something that's not in the array. Let's say 101, just to check this works. And yes, as 101 is not in the array, our sequential search has returned -1, indicating that it doesn't exist. Okay, so this is obviously with a smaller array. Try it out with your large arrays, the 1,000 and the 100,000 elements. And also then, once you've done that, have a go at the binary search algorithm as the final exercise 7. Okay, so see how you get on with that.